Can you hear me now? Okay. Yeah, so hi everyone. My name is Ilya. I'm currently a postdoc at Caltech, but I soon will start my own theory group in Varlan University. So we are interested in non-equilibrium control of quantum materials, and in particular Floquet engineering. And today I will tell you how to use Floquet engineering using coherent phonon beams to induce non-equilibrium phases, and in particular I will demonstrate the quantized acoustoelectric effect in quantum nanowires. So let me start by briefly introducing the concept of Floquet engineering. And the idea is that we can modify the properties of the materials by driving them with time periodic fields. So for Floquet engineering of solids, we usually apply strong laser fields, and that has been shown to be a very powerful tool to induce various non-equilibrium phases, including topological states in graphene, modulation of spin exchange interactions in magnetic materials, and that gave rise to various exotic magnetic phases. And there are several theoretical proposals for exotic Floquet phases, including metal-to-insulator transitions, spontaneous breaking of symmetries, and anomalous transport. So these phases are generated using lasers, so basically through oscillating in time electromagnetic field that provides the periodic drive for the electrons. And today I'll tell you about less conventional methods where we drive the material with coherent phonons, and the phonons provide both periodicity in time, but also periodicity in space due to their large momentum. So to use coherent phonons for Floquet engineering of materials, we typically need strong phonon beams, basically high energy phonons in the terahertz range. So those are challenging to generate. So for example, low energy phonons in gigahertz we can generate using piezoelectric elements. But terahertz phonons require different mechanisms, and the most common way to generate terahertz phonons is through optical generation, where we basically illuminate a material with a beam with a pulse of laser, and that through various microscopic mechanisms can generate a terahertz phonon beam. So, and the most common mechanism is basically the laser creates a displacement of the charge, and this charge starts vibrating in terahertz. So another method to generate coherent terahertz phonons is the phonon lasers, and we are actively exploring this direction. So in the phonon lasers, the coherent phonons can be generated through stimulated emission, and that gives rise to much more precise and controlled way to generate strong phonon beams. And we have proposed several setups where we can realize these coherent phonons, where we can realize phonon lasers, and if you're interested, I'll be happy to discuss it later. But today I'll tell you about an application of coherent phonons, how we can use them to generate, to do Floquet engineering in materials, and in particular, I'll demonstrate a phase which exhibits persistent quantized current in a quantum nanowire. And this phase relies on the momentum and energy that is provided from the phonons to the electrons, and therefore it cannot be realized just by laser. So the setup is the following. We have a carbon nanotube, which is driven by an acoustic wave that propagates from the terahertz source on the right to the absorbing material on the left. And the Hamiltonian that describes the system is given here. So H naught describes the unperturbed Hamiltonian of the carbon nanotube, and the cosine term is the propagating wave. So we consider a single volt carbon nanotube that has the following spectrum. And we assume that the doping is near the charge neutrality, so it's lightly doped system, such that the low energy physics can be just described by the parabola in the bottom of this conduction band. So let's zoom in on this parabola. And now let's understand how the spectrum would look like in the presence of this periodic perturbation. So the electrons in this parabola can absorb a phonon from the drive, and therefore we need to draw a replica of this band shifted by the momentum of the phonon and by the momentum and the energy of the phonon. So this replica band represents electrons with a single phonon absorption. And similarly, the electrons can absorb or emit any number of phonons, and therefore we need to draw many replicas like this, and that gives rise to this complicated structure of bands that intersect each other, and at the level crossings, the drive will open a gap, and now we arrive at this very unusual spectrum, Loquet spectrum of the system, which has a lot of bands that cross each other at high energies, but the lower energy band is separated from the rest of the spectrum by a gap. And most interestingly, this lower band has a net field, which is given by omega over q. So if we can create a state where all the electrons occupy only the lower band, that will give rise to a persistent current, which can be found just by integrating over all the group velocities of the occupied states, and that would give rise to a quantized value which is given in the units of the charge of the electron and the frequency of the phonon. So this would be the ideal state that we would like to have. However, this system is not in equilibrium because it is driven, and therefore the electrons can scatter. So the scattering would be due to electron-electron interaction or the interaction with incoherent vibrations of the carbon nanotube, and that will give rise to excitations to the upper band, which is also known as heating. So these are the possible processes that, by the way, can I use, this is a laser? No? Sorry? Oh, never mind. So so those are all the possible scattering processes in the system. So the left figure shows the scattering processes due to electron phonon scattering. And for example, process number 5 will excite electrons from the lower band to the upper band, and process number 1 will do the opposite. It will relax the electrons back to the ground state. And similarly, we can also have excitation processes due to electron-electron interactions, and those would be 2 electron processes. So the goal of our project was to find conditions on the drive such that the system would be close to the ideal state, right, where the electrons are occupying only the lower band. And for example, if the drive is very strong, the gap would be large, and that means that the probability for excitations will be suppressed. So we, in our numerical calculation, we actually calculated the actual steady state of the electrons in the presence of these excitation and relaxation processes, and we calculated the rate for these processes using the Fermi's golden rule, which has to be modified because these are scatterings between the Fourier states, so they have a different structure and time. And this is the actual solution of the steady state calculation. So here the yellow color is occupied state, blue color is the unoccupied state. And you can see that when the gap is small, there are excitations in the upper band, and that means that current will not be quantized. Whereas if the gap is large, we get exactly the ideal steady state, and the current will be quantized. Okay, so this is the actual current as a function of the amplitude of the drive, and indeed you can see that when the driving amplitude is very small, the current is non-quantized, but when the amplitude is large, the current reaches the quantized value of E omega over pi. And we did it for a few values of the dielectric coefficient. The dielectric coefficient screens the electron-electron interactions and therefore reduces the rate of excitation. So if the dielectric coefficient is large, that means that the screening is more efficient and the current reaches 1 faster. Okay, so let me summarize. So I demonstrated that we can use coherent phonon drives to induce novel non-equilibrium phenomena. And in particular, I demonstrated that the coherent phonons can induce a phase with a quantized persistent current in quantum nanowires. And this phase has various applications. So for example, it can be used in metrology, but we can also use this device as a detector for coherent phonons using transport. So basically, if we drive our system with coherent phonons, that means that the current should be quantized. Okay, so thank you.
Thank you. Yeah?
I didn't understand at the beginning why your phonons need to be terahertz.
Well, yeah, so you basically want the phonons to be sort of in the same energy range as the electrons, right? And also you can see that the current would be the current would be proportional to E times omega. So if you use, you can also use, so there are actually experiments that use very, very low, like megahertz phonons. And there in principle, you should see quantized current, but it would be super weak.
Well, it's probably not the focus of your talk, but do you know what happens if you take into account the boundaries of the event?
I see. Yeah, so if I don't focus on the low energy, I mean. Yeah, so in principle, so that's an interesting question. So in principle, you would have additional heating processes because you sort of go to these Umlauf terms. But as long as, like probably what you mean is that we also want the Fermi surface to be much higher, right? We want it to be sort of the order of the Brillouin zone size. Yeah, so I guess for that you need much stronger drives to see the effect. But it would be an interesting regime to explore.
Thank you. There is no further question. Let's thank all the speakers of this session.
Yeah, there's an announcement. So again, regarding the excursion tomorrow afternoon, please look into your email inbox because Nikolai sent a Wednesday, sorry.